This is a course on Embedded Systems Laboratory. This course is a part of the theory course that is associated with that is Embedded Systems. In this lab, we are having two parts. One is the programs we are going to write in terms of assembly language, and this part B is considered with respect to the hardware interfacing, that is with respect to C program. Now in this session, let us try to understand the programs associated with part A. The first program is, the aim of the first program is ALP to multiply two 16-bit numbers. In this program, we are going to multiply two 16-bit numbers and we are storing the result in a register. Here, the data is loaded with respect to two variables. The one is num1 and the second one is num2. These two are the variables, followed by the assembler directive DCD, define constant data of 0x1234. This is the data, 16-bit data. That is, if you write in terms of 0x, that denotes the hexadecimal value, and the second hexadecimal value is related to the variable num2, followed by the assembler directive DCD, define constant data 5678, and we have entry into the program and start the program, and LDR here implies load data from register. We are loading the data from memory to register. Num1 is associated with respect to the memory location. The variable num1 is associated in the memory location, and we are fetching that data 1234 which is residing in the memory location. For example, let us say 1 followed by 7 zeros. This is the memory location. This memory location contains the data 1, 2, 3, 4. Similarly, the next memory location, that is 1, 0, 0, 1, will be having the second data, that is 5, 6, 7, 8. After that, after fetching the data into R0 and R1 respectively, next we are going to multiply the multiplier and multiplicand and store the result in R2. This implies R2 is equal to R0 into R1. R0 into R1 with respect to multiplication. And then what happens? 1, 2, 3, 4 is multiplied with 5, 6, 7, 8, and the result. This is the first 16-bit data, and this is the second 16-bit data. 16-bit data into 16-bit data, the product may go up to 32-bit data. That is n into n grow up to 2n. If you try to multiply an n-bit data with another n-bit data, the width of the product may go up to 2n. In this case, it is n is equal to 16, n is equal to 16, 16-bit into 16-bit, it is going to give a product of 32-bit. Before we start writing any program, this is very important. You have to write the words. You have to write first area followed by the program name, that is multiply, and this is the code, not the data, and read only. Here the term read only refers to we are only reading the data and we are not writing the data. For the sake of simplicity, I have shown here the case of writing the data. After computation, the result is 06260060, which is a 32-bit data which is stored in R2. The next program is an ALP to find the sum of first 10 integer numbers. As usual, we can see area followed by sum. This is the program name, followed by code. This is the code, and this implies with respect to read only. Starting from entry, we have move R1 comma #10. This is the counter value to indicate the first 10 integer numbers. Here our aim is to add first 10 integer numbers. For that purpose, I have taken 10 in terms of immediate data with respect to the immediate addressing mode, and I am trying to move into a register R1. You can write count and move R2 comma hash 0. This is for the purpose of storing the result in R2. This implies that initially the result is 0. To store the sum. And next we have incorporated several instructions inside a loop. The first is, here we are making use of the add instruction, that is add R2 comma R1. This is a 3 operand instruction in which R2 and R1, the contents of R2 and R1 are added and stored in the destination register R2. Here you know that R2 is equal to 0 before execution and R1 is equal to 10 before execution. Here we can write after execution. Now what happens? R2 is equal to R2 plus R1. R2 is equal to 0. R1 is equal to 10. 0 plus 10, 10. So R2 after execution will become 10. Okay. And after adding, we have to decrement the count. That is by using subs R1 comma hash 0x1. One may ask a question that why can't we use sub instead of subs? The answer is, the difference between sub and subs is that sub performs only the subtraction, that is destination is equal to destination minus source, and it is going to update the destination, whereas subs not only updates the difference, not only updates the result, as well as it affects the status flag also. After subtracting the two values, there might be a change in the result, that is if the result is 0, then 0 flag will be affected. If the MSP is equal to 1, then the sign flag is affected, like that. Okay. For the purpose, we are using subs. In particular, here to check the status of 0 flag. What is the status of the 0 flag? Then what happens? R1 will be decremented by 1. As in case of 8085 or 8086, we don't have the decrement operation, that is DEC for decrement and INC for increment in ARM processor. For that purpose, we have to replace DEC by SUB and INC increment by ADD, addition and subtraction. Then R1 is subtracted by 1. Then what is the value of R1 before execution? Now it is 10. After execution, R1 will be equal to 9. Okay. Then check the condition. Branch if not equal to. Branch if not equal to. That means here after subtracting the contents of 10 by 1, not equal to refers to has it affected 0 flag. Is 10 minus 1, 9 is equal to 0? 9 is not equal to 0. In this case, it has to go back to the loop. And once again, take the next cycle, that is add R2 comma R1. In this cycle, what happens? R2 is equal to, now R2 is equal to 10 and R1 is equal to 9. Now what happens? R2 is equal to R2 plus R1, that is 10 plus 9, that is 19, that will be stored in R2. Now R2 is equal to 19, updated to 19, and next instruction is subtraction instruction, that is affecting the R1. Before execution, R1 was 9, now 9 minus 1, 8, 8 not equal to 0, you can write here 8 not equal to 0, so branch if not equal to Then if it is not equal to 0, then go back to loop and continue the same process till the last cycle. Let us assume, for instance, now the value of R1 is 1, and in the last cycle 1 minus 1, it is equal to 0. Then it comes out of the loop, performing no operation followed by end. Like this, the process will be continued till we get the result of first 10 numbers. Okay. The next program is enable to find the number of zeros and ones in a 32-bit data. Here we are going to find out the number of ones and zeros in a given 32-bit data. Here the term ones and zeros refers to the data in terms of binary. If the given data is in binary, then only we can determine the number of ones and zeros. Okay. As usual, area count 0, 1 for counting zeros and ones. Code, this is the code, and we are going to just read the data, read only. Here first let us consider a data that is 32-bit data by using the assembler directive by variable num dcd define constant data followed by 0x. Here the term 0x denotes hexadecimal. If you write any data with respect to 0x, then it is considered as hexadecimal data. 1, 2, 3, 4, 5, 6, 7, 8. I have taken the 32-bit data. This in turn can be written in terms of binary like 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, double 0, 0, 1, 0, 1. This is the 32-bit data in terms of binary entry. From here the code starts. Move R0, hash 0. Here we are using the immediate addressing mode, and we are storing the 0 in terms of, we are storing the 0 into R0. That means here we are maintaining the counter for number of zeros. Counter for zeros. And similarly, R1 move R1, hash 0, counter for number of ones, and move R2, hash 32. Since we have to test 32-bit data, each bit. So how many bits we have to test? We have to test 32-bit data. Each bit is tested individually. For that purpose, this is the count. We can write the 32 in terms of hexadecimal also. In this case, we can write hash 0x20. The hexadecimal value for 32 is 20. If you want, you can use 0x20 or you can use 32. Both are acceptable. And next, LDR R2, num. We are getting the value from memory with respect to the variable num, that is referring to the 1, 2, 3, 4, 5, 6, 7, 8, and then we are storing into R2. And then using the logical shift right instruction, we are going to shift the data towards right by 1 position. And the term yes, logical shift right, yes, here yes implies status flag. Here we are considering the status flag of carry. We are worried about the status of carry. What is the status of carry? After shifting the data towards right logically by 1 bit position, and then we have to check the status of carry, if the carry is set or reset. Then branch to the label next branch. This is BCS, it is branch, short branch. Okay, branch to next if carry is set. The C implies here is carry is set. If any carry is obtained with respect, if any carry is seen out of the LSB then this is going to work. That is PCS next. If there is any carry, then it goes to next. If there is carry, you have to take the account of number of ones. Number of ones has to be incremented. For that purpose, it comes here. Next, add R1 comma R1 comma hash 1. Before execution, what is the value of R1? R1 is 0. If suppose let us assume that the carry is generated, the status flag is set, then R0 is equal to R1 is equal to R1 plus 1. That is 0 plus 1. Okay. But in this case, the bit moved out of the LSB is, we are trying to shift towards right, and the bit moved out of the LSB is 0. So what is the carry flag? The status of the carry flag? The status of the carry flag is reset. Okay. The status of the carry flag is reset. So in that case, it is not going to the next. It is continuing the immediate instruction followed by BCS, that is add R0 comma hash 1. Then we have to update the contents of R0. Since there is no carry, we have to update R0. R0 is equal to 0 plus 1. That is the R1 case is just to show that the carry is set, assuming that carry is set. But in this case, in this example, the carry is reset. For simplicity, let us not consider. We are consider only R0. Okay. And then it goes to the next instruction. The next instruction is branch to skip. It comes here. Okay. Why it is going here? Because we are checking ones or zeros, and we found that 0 is the output with respect to the carry flag, and no need to work out this condition. That is either 0 or 1. If you continue with respect to this instruction, then what happens? Each time R1 will also be updating, and R0 will also be updating. In order to avoid that, we are skipping that instruction and going to the next instruction. The next instruction says that subtract R3 comma hash 1. The count is associated with the R3. Sorry, that is not R3, that is actually R2. That is here it is R2. Okay, because R3 is nowhere else we have taken. Similarly, here also it becomes R2. Okay, subtract R2 by 1. 32 minus 1, that is 31. Okay. And then comparing R2 comma 0. We are comparing this subtracted value, the output of the subtracted value 31 with 0. Is it equal to 0? No, not equal to 0. That means in the previous program we have used SUBS, that is subtract and then update the status flag, that is 0 flag. Here we are using only SUB, we are not using SUBS. For that purpose we have to incorporate one more instruction, that is compare R2 comma hash 0. Here we are comparing the difference with 0. If it is equal to 0, we will continue with respect to the next instruction. If it is not equal to 0, then we are going to the loop. It is branch if not equal. Yes, not equal. 31 not equal to 0. Then it has to go back to the label back. That is here. The next cycle, logical shift right with affecting the status flag. Then after this 0, next this 0 is coming out. Like that the process repeats till all the 32-bit data is checked individually for ones and zeros. And here with respect to this instruction, that is LSRS R2 comma hash 1, we can have an alternative instruction, that is ROR. ROR can be alternatively used LSR Why we are choosing this instead of ROR is shifting is comparatively easy than rotating. Okay. What happens here if you use rotate instruction? Here also we are seeing that in rotate what happens? The bit moved out of the LSB is occupied by the MSB where the vacancy is created. When this bit comes here, the vacancy is created. That vacancy is filled by the bit moved out of the LSB. Since rotating is comparatively difficult with respect to the shift, we are using shift and not using rotate instruction. Okay. Like this, all the 32-bit data is checked, and then once this R2 is equal to 0 after the subtraction, then it comes out of the loop and performs no operation and the program is ended. In this case, the number of ones is, there are 13 ones, meaning is 19 zeros. Zeros is taken into account of R0. 19 plus 13 we get 30. Like this the program goes. The next program is the fourth program, that is ALP to determine whether the given 16-bit number is even or odd. In this program we are going to determine the given 16-bit data whether it is a even number or odd number based on the logic. The logic is, in this we are going to take a 16-bit data, and we all know that in order to determine whether the given number is even or odd, there are two logics. The first logic is using rotate right or shift right, that is we can use LSRS or ROR. What happens if you shift the data towards right? The LSB will comes out of the data, will comes out and it is affecting the carry flag. If the carry is set, we know that the given data is even number. If the carry is reset, if 0 comes out of the LSB, then it is treated as odd number. The second logic is divide by 2 logic. Divide by 2 logic. What this logic implies? Here we are going to take a data and we are using the division operation. We are going to divide the given data by 2 and check the remainder. If the remainder is 1, we can come to the conclusion that the data is odd. If the remainder is 0, then we can come to the conclusion that the given data is even. For sake of simplicity, here we are not trying this second logic, that is divided by 2 logic. We are working out with respect to the first logic, that is by using shift or rotate instruction. Now let us try to analyze the program. As usual, here area followed by the code name, that is even odd code. This is read only as usual. Here first we are going to define the 16-bit data using the variable num, assembler directive BCD followed by 0x BEEC. We have taken a 16-bit data, that is BEEC, and we are trying to find whether this BEEC is odd or even. Move R1 comma num. What happens in this instruction? The data BEEC will be moved into R1. Okay. Alternatively, one may use the LDR R1 comma. Okay. If you want to use LDR, otherwise you can use MOV instruction. Then logical shift right by affecting the status flag contents of R1 by 1 bit position. First, let us try to write this data in terms of binary. B is 12, sorry, B is 11, it is 11, 8 plus 2, 10, 10 plus 1, 11, and E is 14, 14 can be written as 8 plus 4, 12, 12 plus 2, 14. Okay. And similarly, one more E, 1, 1, 0, and C is 12, 1, 1, 0, 0. Here we are checking the LSB. The LSB is 0. After you perform rotate or logical shift right, then what happens? The bit coming out of the LSB is 0. That means here the carry flag is reset, not set, and giving the conclusion that the given data is even number. Okay. For the sake of simplicity, if the given data is even, we are trying to show. For the sake of simplicity, if the given data is even, we are trying to store the value EEE in R0. If the given data is odd, we are trying to store DDD in R0. If the after execution the contents of R0 is EEE, then the given 16-bit number is even. If it is DDD, the given 16-bit number is odd. For that purpose, we have taken E and D. LSRS, that is shifting right by 1 bit position. Then what happens? The bit moved out of the LSB is 0. BCS next. That means branch to next if carry is set. In this case, carry is not set. It is reset. Okay. It is reset. Then it is not going to work out with respect to the label. Next, it is going to work the next immediate instruction, that is move R0, hash 0x EEE. That means the given data is even. Then that's it. We have to stop the program. We are not supposed to work out the move R0, DD. For that purpose, in previous case, we have used B skip. In this case, B stop. Okay. We are going to end the program. B stop. Then this comes here, stop. With respect to the label stop, we have no operation. NOP and then end. Now let us take one more example, that is 1, 2, 3, 5. By looking to this data, one may say that this is a odd. You can write in terms of binary. Okay, 1, 2, 3, 5 expressed in terms of binary. And what is the LSB here? LSB is 1. What happens when you shift or write? Then the bit which is coming out of the LSB is 1, whereby carry flag is set. Carry flag is set. BCS next. Branch if carry flag is set. Yes, of course, in this case carry flag is set. Then it comes here next and tries to load the immediate data DDD into R0, indicating the given data is odd number. Okay. The next program is the fifth program, ALP to write data to RAM. Here the aim is to write a data into a RAM. Into RAM refers to RAM location. We are going to read the data first and then we are going to write the data into memory location, which is nothing but RAM location. For that, as usual, area, the code name is data write. We are going to write the data for that purpose. Data write, code read only. First, for this, first we are reading the data. We have mentioned as read only. Entry data. First, since the program has no indication with respect to the size of the data, the size of the data is not mentioned. Size of the data to be written inside the memory location is not mentioned. For sake of simplicity, let us try to take a 32-bit data. 32-bit data we have taken. We are trying to move that 32-bit data into a memory location by using the assembler directive DCD, that is variable data DCD 0x 1 2 3 4 5 6 7 8. This is the 32-bit data we are going to write into memory location. LDR, first we have to fetch the data from memory to the register. From memory to register R0. The data comes into R0. Then LDR R1 is equal to RAM location. We are assigning a variable name. This is source. R0 is source. And R1 is destination, which is nothing but memory location. In other words, we can call it as the variable RAM location. LDR R1 is equal to RAM location. The variable is RAM location, that is given with respect to the register R1. STR R0 content of R1. That means we are going to write the contents of R0 into R1 with respect to the variable RAM location. The address of the RAM location, the variable RAM location, is dynamically allocated at the runtime. At the runtime in your Keel microvision tool. Okay. And then for purpose of writing, here you can notice the difference here. Here read only, here read write. We are writing after reading in the previous part. Area RAM, because of we are writing the data into RAM. For that purpose I have taken RAM. Here this is data, not code. Here the program, for that purpose we have written code. Here it is data. We are writing the data. For that purpose we have to change this as data. And here instead of read only we have to use read write. The variable is present here. The RAM location DCD is initialized with 0. Before execution we don't know what is the value that is containing in the RAM location with respect to the dynamically allocating the address of RAM location. For simplicity, we will assume that the address for RAM location at runtime is equal to 1 followed by 7 zeros. This is the address of what? RAM location, that is nothing but R1, which is indirect address. After execution, what happens? The content of R0 is what? 1, 2, 3, 4, 5, 6, 7, 8. This content is placed inside the memory location 1 followed by 7 zeros. After execution, the value inside this memory location will be 1, 2, 3, 4, 5, 6, 7, 8. Like this, we are going to write a data into RAM location with respect to two parts. First, we have to write the code, which is nothing but read only, and then we have to write the format of writing the data into memory location. That is, the next step is code is replaced by data and read only is replaced by read write. Like this, we are going to write the data into